here's a few things directly from the code. This chapter talks about wire tables and determination conductor sizes. Very quick, very quick. When we size wires, you're going to size the wires based on a few things, guys. Number one, when we size wires, as you're going to size it based on load. Load, and typically you multiply it by 1.25 because it's continuous, right? That's a load. Size number two, voltage drop, right? The size number two, you're going to do a voltage drop calculation for the wire and size based on voltage drop, right? Number three, you need to do derating. Derating based on temp or bonding. Bonding, right? And I'm not saying anything that you guys don't know. When we size conductor, you have to do three calculations. Calculation number one is based on the load. That's easy. So really is no difference. You take your load, full load amp, multiply by 1.25, size your conductor. No gimmick, nothing. Let me tell you one little thing. So suppose this calculation came up with 4 amp. True, I did calculation and came up the first calculation, Andrew came up with 4 amp. Suppose the voltage drop calculation came up with 250 kcm. Right? I did calculation based on voltage drop and I came up with 250 kcm. Suppose I did derating because I hired Jeff to do the electrical work for me, and he dumped all these branch circuits and feeders, in this case feeders, dumped them in one big fat big conduit. So I have to do it, and to add salt to injury, you put them outdoor where the ambient temperature could be 110. So you have to do it, right? On the roof, which means even worse, you have to add reflected heat. So suppose because of all this, baby, you end up with is 350 kcm. Who's my genius that's going to tell me which size is going to rule? If these three calculations for the same load came up with three different numbers, which one are you going to pick? The largest or the smallest? The largest. Which one is the safest conductor one? The largest. If you forget that one, you're in trouble. So when you do the calculation, three calculations, you're going to pick the one that gets you the largest. No give it nothing. Any comments, any questions about this? So remember that. You're going to do what we did, most of the stuff we did, guys, on calculation. We did the rating before. So if you come up with a number higher than what the Quran, you're going to go to the rating. If you did voltage drop 250, you're going to choose the largest size. That's it. When it comes to the calculation. Can I have thumbs up, chat? We understand you have to use the largest size. Okay. When you do the calculation, you have to use the largest size. Okay, so that's what's the objective of this one? Conductor from the proper wire tables. Being able to use the conductor table. This is a review for all of you guys, I hope so. Otherwise, you need a refund from your friend, Jeff. This is the different types of wire insulation. So that's when we start talking about T, H, H, N, and T, H, H, W, right? The different insulation. Determine installation characteristics, meaning can I install a THHN in a wet location? I hope not. Can I install a THHW in a wet location? Yes, you can. So that's the characteristic of these. Correction and adjustment factor to determine the efficiency of the conductor. There are two of them. One based on ambient temperature, and the other one is based on bonding. Here's the rule. When you guys become estimators and project managers, always put the feeders in separate conduits. When you have a feeder, the worst thing that could happen to you, Darren, is you grab 2 feeders, 200 amp each, and put them in the same conduit. Not a good idea. If you have a feeder, dedicated conduits. Oh, if you load, the only time that it makes sense, Jeff, to group things, the only time it makes sense to group things if they're branch circuits, and if you're feeding them with number 12 or number 10. That's when it makes a lot of sense to group them. So if I have a 3-phase motor, and that 3-phase motor did the calculation in it, and you need 3 conductors, number 10. shoot that one, and there's another motor right next to it that also need another 3 conductors number 10. Very good idea to put these 6 conductors number 10 with an equivalent ground conductor in one conduit, say 3/4 of an inch empty, and shoot them all the way to that location, to a junction box, let them there, and feed the two loads. That's where it makes sense to group things. Can I have thumbs up, chat, when it makes sense to group things? If you're feeding with number 12 or number 10, it doesn't make a lot of sense, guys, to start grouping if you have number 10, maybe number 8 at the border, but higher than that, number 6, dedicated branch circuit. You have a number 6 for a 3-phase load, dedicated branch circuit. Okay, these are opinion though. The code-wise, you can group anything you want. Definitely, you don't want to group any feeder that's 100 or branch circuit that's 100 amp or more. You don't want to group it with anything else. It's just not a good idea. Determine the resistance of long length. This with the resistance, decide the voltage drop. We'll talk about the calculation for it. Determine proper size, wire size for load located long distance from the source. That's a voltage drop. List the requirement for using parallel conductor, which you guys already have done that with your friend Chad. We're going to remind you of the rules for parallel conductors. When you become a project manager, if you're an electrical designer, guys, you will never hear this. If you're a project manager, you're going to hear the term mega ohm meter. When you install the electrical system, before you energize it and blow up half of the building and get sued and get fired, you would hope that somebody will measure all these feeders. So what they do, guys, is they measure the feeders. When you measure the feeders, you measure the installation of all these, especially the feeders, Jeff, at least the feeders. All the feeders, you measure them, meaning you measure the installation. That will, if you, while you're installing it, because Darren is kind of a tough guy, while he's pulling 500 kcm conductor, he damaged the installation. Now you have ground fault in it. You can't tell unless you measure them. If you measure them, you take the phase A that's grounded to the conduit, and you measure them, it will show you very low impedance, low resistance. That's an indication, my friend, that you have a ground fault on phase A on that particular feeder. So most of the project, high-profile project, hospitals, sport arenas, part of the commissioning the building, they call it commissioning the building, guys, is to, before they energize them, part of the commissioning before they energize is to measure it. You'll look at it in a second here. That's a big deal. Huh? If it's bad? Yeah, well, it's better discovering it at this point than energizing, and you got yourself a ground fault, and our ground fault could, nobody's going to get hurt, but you burn part of the equipment, you have to go replace it. That's what I thought. Measuring it and figuring the ground fault in the short circuit, guys, is much better than downstream discovering that one. Okay, Article 310, guys, is the most famous, and then you see we'll talk about conductors. List of all conductor application, allowable ampacity, given installation. We'll talk about this one. Determine the conductor size, all from Article 310. Correcting factor for anything other than 50 degrees Celsius, anything higher or lower, or more than 4 or more than 3 current conductors in a conduit, you have to do it. So all this derating, temperature, and ampacity is coming from 310. If you don't know that, I hope, guys, this is your last semester with us. We did 2 projects already. I really do hope that we did some with Gary. You understand that everything is related to the conductors in Article 110. Give you the ampacity of the conductor plus the ability to derate based on bundling, more than 3 conductors, or based on temperature, or both. Okay, installation type, amount of current conductor carries, voltage rating. When we say THHM, guys, the amount of current a conductor can carry as well as the voltage, these are 600 volts rated typically, so that's voltage rated. So if I have carry a 15,000 volt system, can I use a THHM? You can if you want to be fired. No, you can't use it. So the amount of current in the conductor will be carried. Typically the amount of current is with the conductive material. The insulation will decide the voltage. The conductor is made out of 2 very important things. Oh, one is the conductive material, and the other one is the insulation. Okay, so typically, my friends, the insulation decides the voltage, the conductive material decides the current. But of course, they both play a role in thicker insulation. Thicker insulation can trap the heat, so then it doesn't carry more current. The problem with the insulation, guys, it insulates the voltage from going somewhere, but at the same time, it traps the heat. If you trap the heat, the best conductor, by the way, is the one that's hanging up in the air, outside, right? No insulation in there, cooled by the air, right? That will carry more current. So if you take say number 10, put it outside, up in the air, hanging, of course, on the pole, versus you putting in an insulation in a conduit, if it's up in the air, it can carry 50% more current almost, or 30% more current than if it's inside the conduit. Why? Because it's cool. Okay, so that's your insulation. The voltage insulation type, withstand, to determine. So type of insulation to the material and thickness of material, that's a major part, guys, in determining the ampacity of the conductor, as well as how much voltage you can hold. And if you have a good example here, if you have an insulation, for example, for a medium voltage cable, this will be thicker insulation for a medium voltage cable than it was for 600 volts. So be aware that the insulation will decide also the amp of the conductor because it traps heat. Okay, so that's basically what it is. Here's your insulation. The problem with the insulation here, it takes the voltage, give you the voltage, at the same time decide the current. This baby typically decide the current only. The copper will decide the current only. Why the insulation decide the current too? Because it traps the heat. More insulation is better, but what's the problem with it? It traps heat. If you trap heat, the conductor gets hotter more, which means you're going to deteriorate the insulation, which means you're going to have ground fault. Any comments, guys, about the voltage and the current effect on the conductive material, aka the copper, or the insulation? Any comments, any questions about that? Any comments, any questions? So everybody knows that, right? The voltage, the insulation decide the voltage and also decide how much current because it traps heat. Okay, determine the ampacity type. So when you find how much current a conductor can carry, a couple of things you have to take into consideration. What type of material you are using? And these are the three types of material, aluminum and copper being the most common application. So either copper or aluminum or copper-clad aluminum. They have a mixture of conductor that has copper and aluminum together. So copper conductors can carry more current for the same cross-section area. Everybody knows that. That's what we like him. Smaller conductor carry more current. So that's the ampacity of the conductor. I hope you know that by now. Correction factor. Ambient temperature. If your ambient temperature is out of that 31 you have to do it. You have to determine the current of the conductor can carry. So other than 30, you have to derate. The code reference these derating factors you will see in a second for reduction. So after you apply the derating factor, that will be the ampacity of that particular conductor. And we'll take a quick example on that one. 3 conductors in a raceway. If you put 3 conductors in a raceway, Jeff, what do? You derate them. I know by now. This is the table that adjusts for derating. Conductors of different systems, installing the conductors in a cable tray, also you have to derate. And the only time you do not derate if you have a little short run of a conduit, 24 inches or less. 24 inches or less. Aaron, do you remember when we did the commercial project and we had a lighting panel right next to it, a commercial lighting panel and lighting control panel? And we said we're going to nibble them together with a 24 inches or less. And you pull all these conductors between the 2 panels, then you don't have to derate. You do not have to derate. Any comments, guys, about derating based on more than 3 conductors in a conduit? Derating based on 3 conductors in a conduit. Any comments, any questions? So that's your derating based on the conduits. Here's the table again. Don't forget to put 310.15b16 here. These are the tables, guys, we use for the ampacity and for underground, conductor ducts for underground. If calculating conductor size and resistance, under engineering supervision, believe it or not, you can also find the derating factor based on the formula. You can use this formula to find the rate based on the temperature instead of using the table. So either use this formula or you use the tables. 99.9% of us use the tables because we don't have software. Okay, the second thing, guys, so this is the ampacity. The second thing is the voltage drop. Voltage drop is determined by the material, the diameter, the thickness, the length of the conductor, also the ambient temperature of the conductor. And if you guys remember, voltage, you have a voltage drop equal to KIL, K-I-L over Cm. So when you have a voltage drop problem, you have to take the current that the conductor can carry, multiplied by the length, multiplied by the factor K, a special factor related to the material, divided by the circular mil of the conductor. That's how you find your voltage drop for single phase circuits. So the higher the current, the more voltage drop you have. The longer the distance, the more voltage drop you have. The bigger the conductor size, the less voltage drop you have. Any comments, guys, about the factor that determine the voltage drop for a conductor? Voltage drop, longer length, more voltage drop. Longer, bigger current, more voltage drop. Faster conductor, less voltage drop. Yes, sir. For the project that we're having right now for the branch circuit, when we did the branch circuit, guys, no. If you look at the size of the building that we have, if you're within 100 feet for branch circuit or less, branch circuits, 100 feet or less, if you look around, almost your equipment all for branch, like lighter receptacle, you're almost covered with 1.25 for continuous load and so forth. The only place that you need to check for voltage drop is parking lot, and we typically for parking lot we pull a bigger conductor anyway, like number 10 or number 8, even though we need number 12. Unless you're talking about big projects, yep. On feeders, typically what we do if you have feeders, big facility, if you have 150,000 square foot building, and you need to take feeders everywhere in that building. Our building is 25,000 square foot. That's a small building, very small building, size-wise. So voltage drop on feeders, if you use 1.25 to size of conductors and use DHHL conductors, you're almost done with, typically, you don't have issue with that. Yeah. Well, a lot of engineers actually use it anyway. They run a calculation, a voltage drop calculation on the load. Not hard. For branch circuits or feeders, you take the full load amp. So if you have a panel, say if you want to do a panel, a three-phase voltage drop equal 1.73 times K times I times L divided by circular mil. So I is 100 amp. L is how many length is far the panel is, say 100 feet, multiplied by K, typically, what is it, 11 something for copper. Circular mil is the number of conductors, say we're using 1 ohm, you find the 1 ohm circular mil, divide them, that'll get you how many voltage drop you have. Obviously, your voltage drop has to be less than 3%, right, for feeders. Less than 3% or less. Cool. But we will do some calculation about voltage drop. We're coming to a voltage drop calculation for branch circuits and feeders. Okay, so that's basically the voltage drop. Here's the formula that we guys use. Two formulas we use for voltage drop. Very, very interesting formula. Formula number 1 is this: voltage drop equal for single phase 2 times, I forgot to do 2, KIL over Cm. For 3 phase, voltage drop for 3 phase, you change the 2 into 1.73 times KIL over Cm. So these are the two formulas they use for single phase voltage drop. Again, we will do calculation for this. There's also a formula that says voltage drop equal REL, R-I-L, 2 REL over 1,000. We will use this calculation, guys, this one and the third one for 3 phase. For voltage drop for 3 phase equal to REL, R-I-L, instead of 2 here, they use 1.73 over Cm. Again, I will come back to these, guys. I will come back to these voltage drop calculation. I have a calculation for voltage drop in the calc. problem. Cool? So I'm not trying to avoid it. But these are really the four formulas that we use for voltage drop. The four formulas that we use for voltage drop. Any comments, guys? Any questions about that? The four formulas that we use. Again, this is for single phase here, single phase. And this is three phase, this is single phase. So you can see the same formula, except if you look at the formula, the only difference between them is these two numbers, right? You look at them, what's the difference between the two formulas? These two numbers, right? Any comments, guys? Any questions? We will do calculation based on these two formulas. Promise you. In our calculation. This is just talks about the three-phase, how three-phase effect. Look how the three-phase makes it smoother. When you add all these three phases together, here's what you get, almost the effect. I don't want to go back to the basics. This is how your signal looks like when you add three-phase with 120-degree phase shift between them, right? And this is very similar to what? To a DC circuit, right? So long story short, without getting into all the details, I hope that you guys will cover this one in the basics. If you have a power system that's very close to the DC, this is very efficient power system. That's why three-phase is efficient, right? Look at that. When you add all these signals, ignore everything else. Just go from here right on this. So as the phase A goes down, phase B takes up. See how they keep the equipment, they keep the voltage right at the reference to the equipment. So long story short, that's where AC guys are superior, AC three-phase superior to AC single phase. Because it's closer in terms of DC. You can see it doesn't go to the zero. Can you see it doesn't go to the zero here? When one is going to the zero, the other is picks up. Like it's like three people are carrying the same load, right? If one is tired and reach the point zero, they shifted it to the other phase. So think of it this way. So that's my three-phase. And that's where this is just telling you is one current is always higher than the other two, goes all the way up. So all together, they equal to, they pick up the load. Okay, here's what I would like you guys to do for parallel conductors. If you don't know this right now, please be aware of it. The conductors must be, with the parallel conductors, they must be the same length. So let's just say 100 feet. All of them must be made of the same material, T, H, N. Must be the same area, 4R. And must have the same type of insulation. Oops. This is T, H, N. Here, this is copper. This one is Cu, copper. This is Cu. And terminated connected to the same in the same manner, so the logs are for all the phases are terminated in the same area. And you can add also conduit if you're put in different conduits, same conduit, like rigid metal conduit. Any question guys about these 6 rules for parallel conductor? You must know that when you have parallel conductors, you have to have the same thing, same material, same size, same insulation, same termination, same conduit if you put them in a conduit. Any comments, any questions? Let's review for all of you, right? When we do, it makes a big deal, guys, when we do takeoff, next section. So when you do your equipment. If you don't do that, Jeffrey, right? If you put one phase A in one steel conduit, it will you created an inductive heater, right? It will induce heat, it's like a transformer. It will induce heat here, induce voltage, and that in turn will induce current here. And long story short, the conduit will be hot. And there's examples, guys, of glowing conduits because of this. And we're not talking about 5 amps here. We're talking about 100, 200, 300 amps going right through that conductor, right in here, 300 amps. And you're putting it in the steel conduit. It will induce enough current and voltage into the conduit, and the current is going to go any currents everywhere. And because the conduit has impedance, you start heating it. You're creating an inductive heater. Any comments, guys? Any questions about that? So your eddy current moving to the conduit. So who wants to have a hot conduit surrounding your conductors? Talk about failure of insulation. Now that's a major failure of insulation. Okay, so that's that. Here's how you find your conductors, guys. When you parallel conductors, you can see phase A, phase B, phase C, conductors from each one of them going to each phase, right? When you parallel conductors, you put phase A, like you see, phase A, phase B, phase C, and a neutral in one conduit. Phase A, phase B, phase C, and a neutral all in one conduit there, right, my friend? You put A, B, and C in the same conduit. Can I put all A conductors in one conduit? When I parallel, can I put the conductor of phase A all in one conduit? Anybody? No, except if you're using PVC. If you're using PVC, then there's no inductive heat. So, but typically it's not practiced though. Okay, testing wiring. We talked about testing wiring. You test for short and long pole test, and you test it with mega ohm meter. Each conductor is tested separately. Here's how you do it. The first thing you do on this side, guys, if there's a machine here, here's my machine, right? The first thing you do, Jeff, is you disconnect the conductor, right? The first thing you do on the other end, you disconnect the conductor. Very, very important. Disconnect the conductor, and then you come over here and you crank that one, basically cranking it. You're sending current right through here. It shouldn't come back because it's not shorted, right? It shouldn't come back. And measuring it back here. If it shows a very high, large infinity, for example, very high, large impedance, this means the insulation is in a good, and there's values for the insulation. Very high value, good insulation. Very low value means you have a short. What do you have? They are shorted together somewhere here, right? That's basically what they do with insulation. Who cares? It will save you tripping on a short circuit or ground fault. The same thing, then you take every phase and the conduit, metallic conduit, of course. Same thing, here's the sending current right here and measuring it back. If the conductor and the conduit are touching each other here, low impedance, low resistance, indicate that you have a ground fault in the system. That's how you measure the equipment if you're a project manager. This is just about the guys, the American wire gauge and how they make the American wire gauge. The way they do them is the number of draws, and they have a nice picture of here. So you start with a big wire over here, and then based on all these draw blocks, you end up with here with 4 arms, for example. And that's how we decide the number of wires in these draws. I'm not going to get into that. All these are typical sizes, guys, wire gauge sizes for different conductors. The wire size from one side, the diameter from the other side, in thousandths of inch diameter. And you guys know that one. So that's basically what I want to talk about. I just want to show you a couple of tables here before I let you run. Okay, so talked about this, all these. Okay, insulation. Okay, here's how you mega ohm meter decides with very high impedance give you good insulation, very low impedance give you bad insulation. Go check it. There's digital ones too. Talk about this one. Okay, the second thing is that talks about is the conductor. This table from 310.104 talks about conductor application and insulation. I'm going to pick on one little thing that you guys probably, let's pick on this one. The first, this will give you the type of the installation, the acronyms that we use, the temperature rating, where can you use it? This is dry and damp location, no wet location. The sizes that you can come from 14 all the way to 2000. Some diameters here and some jackets that you can do. So if anybody ever asks you, can I use RHW in a wet location? And you go, no. Where do you go? You will go to this table, here's RHW. Does it say dry and wet location? Yes. Then it can be used in wet location. Can you have thumbs up, Chad, how to use this table, especially not the electrician, but everybody else? You know how to use this table? Really, if I give you any installation that you don't know, you go to this table, look at the column, does it say dry or wet? And at what temperature? For example, if you're using RHW2, it's rated for 90 degrees, both wet and dry. if you're using RHW rated for 75 only, 75 only for dry and wet. Does that make sense? How to use this table, especially then when you will pass your master exam, we love it. The state love to test you on that. Really not rocket science. So that's okay. 310 very, very simple. Again, I'm going to touch on that one because we guys have done this before. If you have not wrote this one before, please do. We talked about default when we use this table. Start here, Chad. We talked about the default for using this table, and we said our default typically is right in here, right? So up to here, you're using 75-degree column, right? So right here. So from here down, you're using 75-degree column, right? So 75, one knot, and larger, you default to 75-degree column. You guys remember that? Number one and smaller, unless you know otherwise. Number one and smaller, unless you know otherwise, you default to 60-degree column. That's the default. In three-phase equipment, Jeff, if you have a three-phase equipment, always your default is always 75. Okay, so when you size equipment, you are in this column right here. So 4 amps can get me 230 amps. Done, 230 amps. Any comments, any question for installation check, THW, or any type of installation that you can use, or XHW, or any type of installation that you can use. You can use rated for 75. You can get the amp for 230 for 4 on. Any comments, any questions? Everybody knows how to use this table, so not a whole lot new about this. Temperature rating, I will go over it one more time for the record here, and then you guys will. Temperature derating, these are new 2011, guys. So for example, I have a 100 amp feeder. I always like this one. And the installation is THHM. So here's 90. And I need to go put that baby in an ambient temperature of 104. The derating factor is 0.91. So you take 100, multiply it by 0.91, and that will get you what? 91 amps. So Jamie, how many amps did I lose? 9 amps. Everybody knows how to use this table? Now, if Aaron is a troublemaker, he said, Chad, no, I don't want to use THHM. I want to use THW, right? Just because. So that will shift you to 75 because H 75, which will go to this factor. Then it becomes 100 times 0.88, and that will get you 88 amps. So you lost more amps. Does that make sense, guys? How to use this table? I hope by now everybody knows how to use it. The derating table. Any comments, any questions? One last example about that one. Suppose, who's another troublemaker here? Brian. Suppose Brian said, no, Chad, I want to use TW. Just for the heck of it, right? I want to use TW. No problem. Use TW. What's the derating factor? 0.82. So 100 times 0.82 equals 82 amps. Now, which one, if you are the smartest, brightest bulb on the tree, which one would you choose if you have a choice? Right? THHM, right? Why? Because you get more amps out of it. Any comments, guys? Any question why we use THHM if we are indoor, dry location? That's the reason why we use THHM. We always defaulted to THHM, if you remember. Not a whole lot. Really not a whole lot. There's application we have to use TW for certain application, but you typically would default to THHM. A lot of them has dual rating THHM/THW, so you can use it indoor. The problem is wet or dry location. If you're indoor, your THHM down. Your outdoor THHM/THW will get you there. So that's your derating factor. So we talked about this one based on this. This is the key factor, guys, for the, we'll use this one in a second when we do a drop. This is the ohm per circular mil for copper, where's my copper? Here's my copper, it's almost 11. And there's the coefficient of temperature correction factor. I'm sure you guys have done that one probably with Gary. We use it in the basic a lot. So when we see the K factor, that's what we talk about, the K factor here. The K factor. We'll use this one when I do voltage drop calculation for you. Okay, voltage drop. If you're doing voltage drop with resistor, which we will be doing that. If you're doing voltage drop with resistor, here's what I would like you guys to do a little bit. So let's just pick, because let's just go to number, for example, number 12. I have number 12 here. Oops, number 12 here. Solid means one conductor, quantity. And I'm going to go, it's a copper, it's uncoated, and the ohm per 1,000 feet is 1.92. This is the R. This is how you find the R for a size of a conductor. Who cares? The question would be who cares? Because you're going to use voltage drop equal to R/I/L over 1,000. So Jeff, where are you going to find the R for the cable? Right here. From this table. If your conductor was stranded, same thing, number 12 stranded here, it gives you this value. So this value goes into R. After larger than number 8, you can see here it becomes all stranded. Any comments, any questions about table 8? We have seen table 8, we will be using it for voltage drop. We will be using it for voltage drop. Any question about table 8 and using it? If you don't know how to use table 8, what do you need to do? Read one from your friend Chad. So when I say go to table 8, again, this is some of this guys' review, but very essential before you leave here to know it. A lot of chances. The refund will be in the case of seeing you next fall. Right here. Not a refund, no thank you. No thanks, huh? Ambient temperature, we got that. Okay, bundling. Bundling. If you bundle more than 3 carrying conductors and you are a knucklehead like your friend Chad, you put 41 conductors in one big fat fluffy conduit, right? How much amps you can get out of each one of them? 35. Take this example. If each one of these conductors, that 35 of them was carrying 10 amps. Each one of them was carrying 10 amps, right? Look what happened to these. There's all of them in one conduit, and there's 41 of them. So then I have 10 amps, multiply this by 0.35. How much amps am I carrying? 3.5 amps. Disaster. Is that disaster or what? A conductor that's supposed to carry 100 amps now is only allowed to carry 3.5 amps. Is that disaster? I think so. Okay, so that's basically, so you got screwed up, basically. So that's my derating factor. We talked about the table. There's other tables that you guys we use in every single book too. This table I'm just going to emphasize. 317. Kerry, my friend, if you decided to pull a conductor, free air based on ambient temperature. So you have an insulation on a pole and you pull your conductor to the top of it, right? That's how we use this table. Look at this. I have so allow them to single insulated conductor up in the air. The 4 look at the 4 up in the air. I can, under 75 degrees, I can pull 360. 360, we just pulled 230 out of it if it was in a conduit. If it wasn't a conduit, guys, 4 was giving us 230, I believe. Now you put it up in the air on a pole, cooled, naturally cooled, you got 360 amps. So that will give you an idea why Excel, when they put all their power lines, they don't put insulation on them. When bringing from Becker all the way to Minneapolis, completely bare naked up in the air, so they can be cooled, right? A day like this, when it's cold, it's perfect for the conductors. A cold day. So that table is for you can tell it's really nice to compare and see how you can do that. Got the conductors, ampacity here. So these are the things I would like guys to just a quick emphasize. Talked about these. That's all I have. Any comments, my friends? Any questions? Please read this chapter. Please do the calculation. The only thing I would like to do out of this chapter, not this week, Jeff, is do voltage drop calculation. Three-phase voltage drop and single-phase voltage drop calculation based on the K and the R. I like the R because the R is always in the code. You don't have to worry about the K if you use the R. That would be part of our calculation. We'll do a voltage drop. Yeah. Can you guys assure me that everybody knows how to pick a conductor, derate the conductor based on all these? Yes? Am I not going too fast on it for a reason? So this is a quick review. For Jeff, it would be the review number 120. Too many of them from the 292 into all this good stuff. For the rest of you guys, it would be review probably number 2 or 3. What? No. Did we? Okay, well, the most important thing is this is it, man. If you don't know it, you're not a designer. Okay, thank you guys. We'll do right by you.